Imagine a factory. It does not sit beside a river or on the outskirts of a city. Instead, it moves through the silent vacuum of space, hundreds of kilometers above the Earth. This orbital facility manufactures specialized goods, advanced semiconductor wafers, pure pharmaceutical crystals. The parts are then sent back down to the surface for use in our hospitals, computers, power grids. This is not science fiction. It is the core premise of space manufacturing. The central idea is that by moving specific industrial processes off our planet, we could significantly reduce certain types of pollution on Earth. The concept rests on a series of clear, interconnected mechanisms. It is not a single, magical solution, but a complex system of trade-offs, constraints, feedback loops. The fundamental mechanism is simple displacement. Certain manufacturing activities, particularly those involving high heat, toxic chemicals, the need for perfect vacuum, create substantial terrestrial pollution. By relocating these specific high-impact steps to an orbital environment, the associated emissions of soot, heavy metals, harmful gases would occur far from Earth's biosphere. The smokestack, in effect, is moved from a populated continent to the near emptiness of low Earth orbit, where its output has a different and potentially less harmful impact. To understand how space manufacturing could affect Earth's pollution, we must first define the system. This system has three primary components: supply source on Earth, processing facility in orbit, demand market back on Earth. The flow begins with raw or semi-finished materials launched from the surface. Launch rockets lifting cargo. In orbit, materials are processed in an orbital factory. Purer crystals for computer chips, fabricated flawless optical fibers. Finished high-value products return in a re-entry capsule. Re-entry capsule landing and recovered cargo. Products sold to consumers and industries. Each stage has distinct inputs, outputs, and constraints. Main participants: private aerospace companies, specialized manufacturing firms, government space agencies, regulatory bodies. Examples: SpaceX, Blue Origin, Rocket Lab. Manufacturing customers: pharmaceutical giants, semiconductor foundries. Government support: NASA, ESA. Regulators set rules: national and international bodies, launch safety regulations, space debris rules, carbon taxes, and economic policy. The central environmental argument for space manufacturing involves a direct trade-off. We would be substituting the continuous ground-level pollution from a terrestrial factory with the episodic high-altitude emissions from rocket launches. A factory on Earth making specialty alloys or semiconductors might operate 24 hours a day, releasing greenhouse gases, volatile organic compounds, other pollutants directly into the lower atmosphere, where they impact local air quality and ecosystems. By moving this process to a solar-powered facility in orbit, these specific emissions are eliminated from the terrestrial environment. The benefit appears clear, cleaner air and water for communities living near industrial zones. However, this benefit is not free. The cost is paid in rocket emissions. Launching the raw materials, factory components, supplies into space requires powerful rockets that burn massive amounts of fuel. Depending on the fuel type, whether kerosene, hydrogen, or methane, rockets release a cocktail of substances including carbon dioxide, water vapor, soot, alumina particles into various layers of the atmosphere. While the total mass of these emissions is currently small compared to global industries like aviation, a future with frequent launches to support a space-based economy would change that calculation significantly. The key question is a quantitative one. Does the pollution avoided on the ground outweigh the pollution created in the sky? This trade-off must be analyzed with precision. It is a matter of accounting. For a given product, we must calculate the total emissions profile of the Earth-based manufacturing process from start to finish. This is variable X. Then we must calculate the emissions from all the rocket launches required to produce that same product in space, which is variable Y. The system achieves a net environmental benefit only if y is demonstrably smaller than x. This calculation must also consider the location and type of emissions. Soot deposited in the stratosphere by rockets may have a different and more potent warming effect than CO2 released at ground level, complicating a simple comparison of tonnage. The break-even point, or threshold, is when the total life cycle emissions for the space-based production route fall below the terrestrial route. This threshold is not fixed. It will shift as technologies evolve. For example, the development of rockets that use cleaner-burning fuels like green hydrogen, or that are powered by electric propulsion systems, could drastically lower the value of Y. Similarly, stricter carbon pricing or pollution regulations on Earth would effectively increase the cost of X, making the space alternative more attractive sooner. The decision to move a factory to space is therefore not a single event, but a dynamic calculation that will be constantly reevaluated as launch technology, energy systems, and environmental policies change. Beyond simply moving factories, a more advanced stage of a space-based economy involves using resources found in space. Asteroids, the moon, iron, nickel, platinum, water ice. The mechanism here is resource substitution. By sourcing these raw materials from celestial bodies, we could reduce the need for destructive and polluting mining operations on Earth. Terrestrial mining is a major source of environmental degradation, responsible for habitat destruction, water contamination from chemical leaching, and massive carbon emissions from heavy machinery and transport. Asteroid mining offers a potential alternative that leaves Earth's vulnerable ecosystems untouched. This futuristic vision is constrained by immense technical and economic hurdles. The first is cost and energy. The energy required to travel to an asteroid, extract materials, and then transport them to a manufacturing hub in Earth orbit or back to Earth's surface is colossal. Current propulsion technologies make this prohibitively expensive for all but the most precious materials, like platinum group metals. A critical threshold is the price per kilogram. For asteroid mining to become viable for bulk materials like iron, the cost of extraction and transport must fall to a level competitive with, or lower than, the cost of digging it out of the ground on Earth, including any environmental taxes. Furthermore, there is a significant infrastructure delay. We currently lack the technology for fully autonomous robotic mining operations in deep space. Developing, testing, and deploying a fleet of asteroid prospecting and mining spacecraft would take decades and require hundreds of billions of dollars in investment. An entire supply chain needs to be built from scratch, orbital refineries that process the raw ore to the transport vehicles that move it. This represents a massive time lag in the system. A positive feedback loop could, however, accelerate this timeline once it starts. Water ice mined from asteroids or the moon can be split into hydrogen and oxygen, the primary components of powerful rocket fuel. Having propellant depots in orbit or on the moon would dramatically lower the cost of all other space activities, as rockets would no longer need to launch from Earth with all the fuel for their entire mission. This in-space refueling capability would make transportation between Earth, the Moon, and asteroids cheaper. Cheaper transport would make more asteroid mining ventures profitable, which would in turn produce more propellant, creating a self-sustaining cycle of economic expansion and infrastructure growth in space. The entire system of space manufacturing will be driven not by environmental ideals alone, but by cold economic logic. Companies will only invest the vast sums of money required if they see a clear path to profitability. The primary incentive is the potential for a superior or cheaper product. For example, in the microgravity of space, it is possible to grow larger, more perfect protein crystals for drug development, or to manufacture ZB-LAN optical fibers that are hundreds of times more efficient than the best silica-based fibers made on Earth. If this higher quality allows a company to dominate a lucrative market, the high initial cost of space production becomes a justifiable investment. This economic calculation is governed by critical thresholds. The most important is the break-even point. An investor needs to know how many years it will take for the higher profits from a space-made product to pay back the enormous upfront cost of the launches and the orbital factory. This payback period might be 10 years, 15 years, even 20 years. A second threshold is regulatory. If governments on Earth implement a price on carbon emissions, high, stable, predictable, the operating cost of a polluting terrestrial factory, variable X, increases. This directly shortens the payback period for a clean, solar-powered space factory, making the investment more attractive. However, the system is fraught with delays that slow down these economic incentives. The first is the technology development timeline. It takes years of R&D to perfect a new manufacturing process for the space environment, and even longer to build and qualify the hardware for flight. The second is the policy delay. Governments are slow to create new laws. The lack of clear international treaties on space resource rights, for instance, creates uncertainty for potential asteroid miners, making investors hesitant to fund such ventures. This policy lag can stall progress for years, even if the technology and the economic case are otherwise ready. A crucial feedback loop in this economic system is market adoption. As the first space-made products, like ultra-pure semiconductors, come to market, they will likely be expensive. If early adopters in high-tech sectors buy these products and demonstrate their superior performance, it creates a market signal. This success validates the business model, attracting more investment, enabling economies of scale, which can slowly bring down prices. This, in turn, expands the market to more customers. Evaluating the total, system-wide effect of space manufacturing reveals a complex and mixed picture. In the best-case scenario, a mature space economy leads to tangible environmental benefits on Earth. The dirtiest steps of high-value manufacturing chains are moved to solar-powered orbital platforms, leading to cleaner air, cleaner water around former industrial centers. This outcome is contingent on critical thresholds. Launch costs must fall dramatically, space-based energy must become efficient, and policies must price terrestrial pollution. Otherwise, only a few low-mass products shift, global pollution impact stays small, rocket emissions and debris risks grow, and the system can stall without strong cost and adoption loops. The final result depends entirely on the numbers in our system equation. The long-term state of the system is not predetermined. It will be the result of a series of choices made over the next 2 decades. The key variables to watch are cost per kilogram to orbit, evolution of international space law, stringency of environmental regulations on Earth. If the launch cost drops below $100 per kilogram by 2035 and a global carbon tax exceeds $200 per ton, the economic case for moving heavy industry into space becomes immensely compelling. If those thresholds are not met, space manufacturing will likely remain a small, specialized niche for the foreseeable future. The system is sensitive to these initial conditions and policy inputs. This leaves us with several open questions that form a cognitive loop for future analysis. What specific industries, beyond semiconductors, pharmaceuticals, have the right profile, high value, low mass, high pollution, to be the next candidates for off-world production? How will societies decide who bears the immense upfront cost and risk of building this new infrastructure? And can our legal and regulatory frameworks evolve quickly enough to manage a commercial expansion into space without creating a tragedy of the commons in orbit? These are the practical, measurable questions we must confront. If you found this analysis valuable, hit that subscribe button for more deep dives. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.